the last lecture we were concentrating on a particular problem, that is a very standard inequality and equality constraint optimization problem. And we devised a penalty function for this, and we computed the gradient of the penalty function, essentially a part of it. So, what we have learned before was that if you can find a global minimum of these penalized problems, then that sequence of global minimizers would go and hit a global minimizers of global minimizer of the original problem, provided the original problem has a global minimizer. I want to warn you and again remind you that there could be problems which would have local minimizers, but not have global minimizers. Now, what I want to stress here is that in general, when you look into a unconstrained problem, say in this case our problem would be our penalized problem would be like this, where P of x, as we have discussed in the last lecture. So, P of x is now this. I would just, I am sure you would remember most of it. Maybe this could be k or p, okay, whatever. So, do not bother about the index numbering there, just some finite number of equality constants and finite number of inequality constants. That is it. So, this Px is what we add here, and now see when you have the, if you have even smooth functions, continuously differentiable functions, this and this, that okay, this is a differentiable function. So, if you add this becomes a differentiable function provided f is so, but it is not so easy to find a global minimizer even if you run certain algorithms, even if you make an application of direct search method about which we will talk very soon, you cannot really get a global minimizer so easily. Finding a global minimizer is a very difficult thing and is a topic of very of current frontier research in optimization. Now, of course, if all these are convex, then of course this is true, but convexity is something we will not assume here at this moment. That is, if you have all this f, gi's and h's, f to be convex, g's to be convex, this to be affine, then of course this would be a convex function which is differentiable, and whatever solution you get of the gradient can be considered as a global minimizer. Now, in general, if I am trying to solve this problem, what I will obtain is, suppose I take rho k, and for each k I am k equal to 1, 2 dot as it goes on, I am evaluating the local minimizer, which I term as xk. And now, let me assume that the local sequence of local minimizer actually converges and converges to some point. So, let me assume that xk goes to some x star. Maybe you can consider xk as a bounded sequence and need not the whole sequence need not go to x star, but there is a subsequence of xk which goes to x star, but that does not matter. So, without loss of generality we can always assume that xk goes to x star. What sort of property you expect out of x star? Is x star a local minimum? The question is if you cannot really conform this, then the next best thing that you can conform is X star a KKT point, Karush-Kuntakar point, or a Fridtjohn point with a normal Fridtjohn multiplier. So, these are the two things. So, this is what you expect, and this is what you would accept. So, there is something called expectation and something called your acceptance means. In real practice, we would just even accept this one. Now, let me tell you, it does not come for free, that you cannot just say that whenever xk goes to x star, I would freely have this condition, freely have this fact. This fact you have to forget for the time being. This fact also you cannot say that you will freely have it. So, what sort of condition you need to satisfy at x star? So, our fundamental assumption is MFCQ holds at x star. That is the Mangasari and Fromovich constant qualification holds at x star. Okay. So, if this holds at x star, then you can guarantee that this is the KKT point. Okay. So, what are we now supposed to do? So, we are supposed to show mathematically that if this happens, then the sequence of local minimizers, these are all local minimizers of this problem now this is an unconstrained problem. So, here you see the attempt is always to convert a constant problem into an unconstant problem and then proceed. Of course, you can say if I have an abstract constant, then this will also remain an unconstant constant problem, but of a slightly lesser degree of work with a, but that does not actually take off the issue. The issue is to make it a unconstant problem, but in real applications you would basically have this sort of thing. Sometimes you have to look into this inclusion, but many cases in engineering applications this x element of u, this x would be nothing but bounds on the variables xi between ai and bi. So, you can again put them into the equality inequality form and work with it. Theoretically you can do it, but when it comes to actual practice you really need to have an unconstant problem, and that is something we need to keep in mind, and that is why I have taken this mode, this problem as our general problem, which maybe you should write as P. So, now if xk is a local minimizer xk is a local minimizer of this problem, then from the very basic optimality condition we know that this fact is known to us. So, what would that imply in our particular case? In our particular case, it would imply grad of f of xk plus rho k, it is a constant, grad of p of xk, and that, so this is nothing but this and this is 0. Now, what is the grad of p of xk? We know already from yesterday's descriptions. So, xk in general is not feasible. So, it will basically become gi xk in most cases. Here also it is not feasible. So, it will become this. And this must be, this whole thing must be equal to 0. We have already computed the derivative of this yesterday, derivative of this part, and this part you can compute easily, it is just a chain rule. So, I just did not compute it. Now, what is important is to do some little bit of manipulation, and so if once we do the manipulation, we have less boards to write, and that is the whole point. Maybe I will, okay, let me just do a little bit of manipulation and write from here. Now, I am coming here and I am writing grad of f x k plus summation lambda k I grad g I x k j is equal, sorry, I is equal to 1 to m plus summation j is equal to 1 to p mu j k grad h j x k equal to 0. Of course, you know that how did I get this lambda I k and how did I get this mu j k. So, you can obviously note this fact that lambda I k is nothing but rho of k, nothing but rho of k, sorry, here it has to be rho of k into this thing, that is rho of k into twice max of g I x k and 0, and this one is this one into rho k, sorry, this, okay, here also have to have the symbol rho k. Excuse me for these slips. So, here of course, mu j k is given as rho k times twice h j x k. So, this part is your rho k into this is your mu j k. So, what we have to prove? We have to prove is that these sequence of vectors are bounded, that is this sequence they form this sequence claim is the following: this sequence is bounded. Actually, what we will show that if it is not bounded, then the Mangasarian form of which constant qualification will be violated in its equality, in its more functional form, its equality form, it will be violated actually. So, you see Mangasarian form of which constant qualification is the key idea in whole of nonlinear programming, and it came out of it came through very simple steps. I think it is a very important idea to go and read the original paper of Mangasarian form of which appeared in Journal of Math Analysis and Applications in 1967. Okay, so let me just rub this part. Let me see what happens if I assume that this claim is false, and we will assume that this is unbounded. So, this is the mathematician's most biggest weapon actually, right, and so the biggest weapon is proof by contradiction. I am assuming something which is contradictory to what I should do, and then I am trying to resolve the matter by coming to some absurd conclusion. So, hence my assumption would be wrong, and whatever I have assumed earlier, what I have claimed has to be true. So, let me assume that this is unbounded. Sorry, lambda k. This sequence is unbounded. So, it means there is a subsequence among these in this sequence whose norm would go to infinity. So, how do we come to such a conclusion? Because if a sequence is bounded, then, or if a sequence has a limit, then every sequence has to have every subsequence, or if a sequence is bounded, then every subsequence is bounded, right. If one of the subsequence is unbounded, then the sequence cannot be bounded. Just P implies Q and negation of Q implies negation of P. That's what we have applied to conclude that if this is unbounded, there is a subsequence here which is unbounded. So, without loss of generality, means without trying to relabel and making the things look bit complex, we assume that, and hence assume, which mathematicians use this symbol very much, without loss of generality, that this norm of this vector I this is going to infinity as k tends to infinity. Okay. Now, once this idea is known, then here we can start making sequences which are bounded. Okay. Now, let me define a sequence of this form. Let me define a sequence, define now define Wk to be of this form for every k. So, Wk is, obviously this is a very big vector. Rather, I should be, I think the symbolism is not really correct. I think I should say, I think the symbolism has to be a bit better, because you see what I want to claim is that I am making a vector out of these. So, basically I should write lambda. See, when I am writing this, I am meaning lambda 1, lambda 2, lambda k. Okay, let me, maybe that will be too bad a shorthand. So, how do I write? Maybe I should write, maybe I will just write this. Let me see, that is much more better, and I'll make the symbolism much more better, because what I here mean is this fact is that lambda k mu k, and I am pretty efficient at making that, is lambda 1 k, lambda m k, mu 1 k, mu p k. Okay. So, that is exactly what I mean by this. If I forgot, I should not have kept the ij. I think that is not a good way of rewriting things. So, this sequence of vectors that I have lambda 1 mu 1 of this form, lambda 2 mu 2 of this form, lambda 3 mu 3 of this form. This sequence I am claiming to be bounded, which I now assume to be unbounded. So, this is, so I now construct a new sequence wk which is of this form. Each element of wk is of this form. Now, if you observe wk is a bounded sequence with each norm wk is of norm 1. So, wk is bounded because since norm wk is 1, and observe that this bounded sequence would have a convergence subsequence. So, without loss of generality, again we can assume that wk converges to some w star. So, without loss of generality, let us assume without loss of generality, let us assume let wk, I should write like this, wk converge to w star. Okay. So, wk converges to w star and norm of w star is 1, which is obvious, and hence this w star is a non-zero vector, it cannot be 0. Now, what I do, how would I handle this thing now? Let me now go and remove the, here I divide all the things by 1 by norm of this. Basically, if you look at wk, if you look at the vector wk, how does it look like? The wk vector looks like the following: lambda 1k norm of lambda k mu k, lambda mk norm of lambda k mu k, right, going on mu 1k divided by norm of lambda k mu k, and mu pk divided by norm of lambda k mu k. This is your wk and this goes to w star. So, w star, these are individually converging to some numbers. So, w star can be written as lambda star lambda bar 1 k lambda bar m k mu bar 1 k mu bar p k, and this lambda I k. So, now limit of where, limit of lambda I k divided by norm of lambda k, lambda k mu k, as k tends to infinity, this is going to lambda bar I k. Similarly, the limit of mu j k divided by norm of lambda k mu k. So, as k goes to infinity, this is going to mu bar j. Sorry, here there is no k, there is no k here, we have taken the sequence limit, so its k is gone. So, this is what is happening. Now, once this happens, it means that here I can do something. So, let me look at this equation, and I am not rubbing this because I want you to remember that that is what these actually this is what it is, this lambda k and mu k if you divide by the norm, etc., whatever. Now, what you do is very simple in the sense that you divide all of these by this number. So, you have 1 by norm of lambda k mu k grad of f of x k plus summation I equal to 1 to m lambda I k divided by norm of lambda k mu k. Okay, this is a k, it is not very clear to you, and that into grad of g I x k. Of course, I am assuming that all the functions are continuously differentiable, they are smooth, that is the gradients are also continuous, plus j is equal to 1 to p mu j k by. So, because this is going to infinity, this norm of this vector is going to infinity, this vector is going to infinity. So, it cannot be all 0, for k sufficiently large it has to be non-zero, right. So, that means that this division is making sense, and so lambda k mu k. In fact, we can assume that okay, this is always a non-zero vector. Again making a mistake in the symbolism, grad h j x k. Now, suppose I take a limit. Now, this is going to infinity. So, this is going to grad f x star. So, this is a bounded sequence, and here is a sequence which is going to 0. So, hence the whole thing here goes to 0. What I am left, so as k tends to infinity, what I am left with is the following. I am left with the fact that summation I is equal to 1 to m lambda bar I grad g I x star, right, plus j is equal to 1 to p mu bar j grad h j x star, that. So, this is equal to 0. Now, you know that this vector w star, which consists of these vectors, is a non-zero vector. So, one among them is non-zero, and that you know violates the Mangasarian-Fromovich constant qualification. Okay, that violates the Mangasarian constant qualification. So, if MFCQ holds at x star, then this cannot have a, this expression cannot hold unless all of these are 0. Here we must have at least one of them non-zero, because w star is of norm 1, that is w star is a non-zero vector. So, hence this implies violation of MFCQ. So, which means that this sequence, they form this is a bounded sequence. So, you see the importance of MFCQ, it makes the Lagrange multipliers bounded, I mean this sort of sequence of multipliers bounded. Now, what happens is the following, that once I know that these are bounded, then once I know that these are bounded, so I know that lambda I k is going to some lambda star I, and okay. So, if once I know this is bounded, then I can assume that lambda I k goes to some lambda star I, as k tends to infinity. Obviously, there is a subsequence which goes, but without loss of generality we will always take a bounded sequence just converges and mu j k and mu j k goes to some mu star j as k tends to infinity. So, as k tends to infinity, what I get is the following. Finally, so as k tends to infinity, what I get here is the following. We get grad of f x k plus summation I is equal to 1 to m lambda star I grad, now this will become x star because x k is going to x star, grad g I x star plus j is equal to 1 to p mu star j grad h j x star is 0. So, one part of the Karush-Kuntaka condition is done. What we need to show is the complementary slackness condition. So, let us see how do we look at the complementary slackness. So, what is now more important is to note the following, that we now have to prove the complementary slackness condition. If I look at the expression, this one, now when lambda I k is going down, you know this rho k cannot be unbounded. If rho k is unbounded, then lambda I k cannot be if rho k, because if I am assuming that lambda I k is converging to lambda star or lambda star I, then I cannot take that rho k is an unbounded sequence, right. We cannot assume that rho k is unbounded, because suppose if I am assuming that rho k is unbounded, then things can just get out of track, because suppose there is a convergent that, so if rho k is unbounded, there is a subsequence among rho k which is whose norm is going to infinity, which immediately means that among the lambda I k there will the corresponding subsequence will go to infinity, right. So, which means that that sequence is also unbounded, because if the sequence has to be bounded, then all the subsequence has to be bounded by the same bound, right. Now, all the subsequence has to be bounded by the same bound. There cannot be any subsequence which is unbounded. If there is one subsequence which is unbounded, it means the subsequence is the sequence is not bounded. So, this is something very important to note, that if I have rho k to be unbounded, then all of the subsequences, there must be a subsequence among rho k which is unbounded. So, which means that lambda I k, all the lambda I k, among the lambda I k, the corresponding subsequence corresponding to the rho k being unbounded, that would also form an unbounded in looking at the structure of the sequence, that will also be unbounded, which will tell me that okay, here I have a subsequence in rho k which is unbounded. So, the sequence cannot be itself be bounded, then that subsequence also has to be bounded. So, that is the very important thing, that if a sequence is bounded, then all the subsequence has to be bounded inside it. There cannot be unbounded subsequence inside a bounded sequence, right. So, which means rho k is bounded. So, rho k, let me assume that rho k goes to let rho k goes to some rho star. So, lambda star I is twice of rho star max being a continuous function, we just take the thing inside. So, Gi x star so whenever Gi x star is strictly less than 0, then okay, now what we have proved is that these sequences are bounded. But we are telling that these are not unbounded sequences. If the sequence is unbounded, then we lose MFCQ at x bar. But remember, when we run a penalty method, then rho k goes to infinity. Rho k itself is an unbounded sequence, but okay, the product etc. makes a bounded sequence. Now, what I have to really prove is the complementarity slackness condition, the last part of the Karush-Kontaveit condition. Now, rho k is unbounded, it looks very strange, and lambda I k is bounded, so it might look very strange to many people. But let us now argue how would we look at it. What we need to do to get the complementary slackness condition. So, we need to know that if I say that this is the set of active indexes for the inequality constant, set of I for which Gi x star is equal to 0. If I know this fact, then what I have? If I know this fact, then I know that if so, let I is not element of I x star, that is Gi x k, so Gi x star is strictly less than 0. Then around x bar, by continuity of the Gi's, there is a ball, and in that ball for all x, Gi x would be strictly less than 0. So, which means for k sufficiently large, if whenever I is not in so whenever I is not in I x star, that is this, whenever I is not in I x star, it implies that for k sufficiently large, Gi x k is strictly less than 0, is also inactive, which means for k when I is not element of, which means thus when I is not in I x star, right, for k sufficiently large, we have, because this is strictly less than 0 for k sufficiently large, because I is not in I x star. So, this max is 0, so this whole thing is 0. We have lambda I k is equal to 0. As k tends to infinity, lambda star I is equal to 0 if I is not element of I x star, and that would give you the complementary slackness condition. You have to think a bit about it. Now, I would like to end up with a question here. This was a very pretty involved argument. Now, the question that I want to end up here is the following, that okay, do you think that this is true, that for most cases, for most situations, when you use this penalty function Px, this penalty function would not in general provide you a solution of the penalty function for rho k very large, because rho k is tending to infinity, may not give you in general a solution of the original problem. That is, if you can keep on increasing rho k, but still the x k that you get may not be feasible and may not be actually a solution of the original problem. What would you, do you think that such a statement would be correct? The problem is that this issue is a major issue in understanding of optimization, that if you use penalty method, the xk that you choose at the end when you stop and choose an xk, that may not be at all feasible to the original problem, and that leads to the study of approximate solution or approximate solution with a certain degree of relaxation, all those things. But what is important, that can we devise a penalty function whose minimization for some large value of k would give me a solution to the original problem under certain very simple natural conditions. That would lead us to the study of what is called exact penalty function that we start tomorrow, but in the exact penalty function we need to have an additional property of the function, that the functions has to be twice continuously differentiable, because we need to use second order sufficient conditions for constant optimization to understand that. But we have not yet done anything about second order sufficient condition. You know, in unconstant case you know that okay, if the Hessian is positive definite, then you will have a local minimum, rather a strict local minimum. But for the constant case we have not told you how to know a local minimum. Suppose you have a Karushkuntagar point, how do you know that that is a local minimum? So that second order condition is something which we will also discuss after giving you a brief idea of how to construct exact penalty function and what could be their what can it give us. We will first derive the second order conditions for sufficient conditions for optimality, and then we will use that idea to show that the exact penalty function can indeed provide us what we really want, that if I solving that problem I will get the solution of the original problem. But the exact penalty function is sometimes also called the Zangwill-Eremin exact penalty function. Zangwill is an American optimizer, while Eremin is a Russian mathematician. The problem that lies largely with exact penalty function that we will see tomorrow is that they would be unbounded. So, not unbounded, they would be non-differentiable, especially at the solutions of the problems. So, this non-differentiability would create a lot of issue, but somehow we would be able to manage through. You will see that nowadays there are a lot of tools to handle non-differentiability. So, that won't become too much of an issue, but theoretically it is a very, very powerful thing, because it tells me that okay, you need not actually bother about the constant problem, you can bother about the unconstant problem, but which is of the non-smooth type, but if you can solve it successfully, then you lead at after certain large k, you will end up with the solution of the actual problem, which is a very, very fascinating result that we will discuss in the next two classes.